Swayam Prabha. Digital India. Educated India.
Essentially, we are saying that for each arm, if the first M pulls of the arm have yielded us S successes and F failures, then according to Bayes' inference, the right thing to do is to maintain a posterior probability distribution, which is the beta distribution with parameters S plus 1 and F plus 1. Okay. To note here, it will look probably slightly different had we started with a different belief at state 0. Right? If that was still a beta distribution, it would sort of be easy to carry out the same steps, because beta is what is called here a conjugate prior, because the prior belief was beta and the posterior remains a beta because of the way the likelihood is coming from a Bernoulli distribution. But in general, it need not be, okay, that these two prior and posterior have the same sort of succinct parametric form. Also to note, had we not been getting Bernoulli samples, had we been getting samples from a different distribution, then, I mean, you'll have to you can't just piggyback on a beta, you'll have to devise different parametric form, if at all possible, right, for your prior and posterior. Sometimes it's just not possible to do. Okay, so for Bernoulli's, this beta correspondence is very convenient. All right, so one more thing, right? We've said for each arm, right, the right way to maintain a belief distribution is to have this beta distribution with the number of successes plus 1, number of failures plus 1 as the prior or the posterior. Now the question is, that's all very well. That's the belief distribution you maintain. But how do you translate having these beliefs into actually deciding which arm you're going to pull? Right? For each arm, you have these beliefs, but then an agent's job, as we've said before, is to take actions, is to pull arms. So what is the principle for deciding to go from there to deciding which arm to pull? Again, that is something that is very elegant. Okay, so once again, if we take all our beta distributions and think of them as one thing, right, rather than n different things, I mean, together they represent a joint probability distribution. And each element of that joint probability distribution is a bandit instance, right? So if you fix each arm's mean, you're fixing a bandit instance. Okay. So what Thompson sampling does is, at any point of time, it has a certain belief distribution over bandit instances. Okay, and it draws a particular bandit instance from this joint probability distribution. So that is achieved by picking each arm of that instance from each corresponding belief distribution for the arms. Okay, but you can think it took in total, right? What is happening is you are basically sampling a bandit instance from your belief distribution. Now, if you've sampled a bandit instance I, right? I mean, this is coming from your belief, probabilistically, of course. What is done next is to simply act as though this is reality, right? Let's take this bandit instance to be the real bandit instance. Had it been the real bandit instance, what would we have done? We would have pulled the optimal arm, right? We would have pulled the arm with the highest mean, true mean. That is the reason we are pulling the arm that gave us the highest sample, XTA. Okay. In some sense, we are acting optimally with respect to this bandit instance that we have sampled from our belief distribution. Now, you can imagine that early on your belief distribution will be hazy. Okay, it's not going to be very accurate. So very often you'll be sampling bandit instances that are quite different from the true bandit instance, right? But that is then allowing you to explore. But with time, what will happen as the beliefs concentrate is you'll be sampling more and more bandit instances that really resemble your bandit instance. Therefore, if you're acting optimally with respect to that, you'll be exploiting, okay, most of the time. So this general principle is also what is usually like implemented even when we're not doing bandits, but for example, dealing with what's called MDPs, which we'll study when we do reinforcement learning, or other types of objects, right, where you have a belief distribution over possible worlds. It seems to be the right thing to do if you want to do regret minimization. Yet another way of looking at what is happening with Thompson sampling is this. Okay, I mean, these two interpretations are maybe related, but take a minute to understand this, right? the probability with which we pick a particular arm, right, to pull is actually our belief that that arm is an optimal arm. So what do I mean by that? Right? Suppose you have a belief distribution and somebody asks you, how much do you believe that arm 2 is an optimal arm or arm 1 is an optimal arm, right? If you're asked, right, then mathematically the correct thing to do is to say, well, I'm going to vary x1, right, which corresponds to my variable for arm 1 from 0 to 1, but I'm going to vary only from 0 to x1, x2, okay, the variable corresponding to arm 2. And write down the PDFs for each of these, right? First is coming from arm 1, the second one is coming from arm 2, dx1, dx2, right? If you do this integral, basically this integral is your belief that arm 1 is better than arm 2, right? But notice that this integral, right, is essentially the probability with which you're going to get this sample x1 to exceed sample x2, right? So, we do it in a sort of computationally convenient way. We draw a sample x1 from the first distribution, a sample x2 from the second distribution, compare them, and then go with the higher sample, right? But that's a way of sampling from this distribution in the sense that we are picking an arm with probability that we believe that it is the optimal arm, okay? And you can actually extend this also if there are multiple arms. You'll have to write down more nested integrals. The reason I didn't do it is because it would go out of the slide, okay? But you can see that this generalizes very easily, okay? All right, so that's quite a bit about Thompson sampling. What's coming up next is more on bandits, okay? I think we are done with the heavy-duty technical stuff as a part of this lecture, but I'll leave you with some thoughts on other ways that people have formulated problems with bandits. All right, students, in this concluding section, let's look at some other questions that have been formulated that are interesting, ones that naturally arise from applications that have to do with bandits, but which are different from what we considered in this class. So what we have considered, I'm sure you are quite familiar by now, is stochastic multi-arm bandits. You have n arms, each corresponds to a reward distribution, and you pull them and get rewards from that probability distribution. And what we've been interested in is to minimize the expected cumulative regret over a certain horizon. All right. So we've seen different algorithms for doing that, but you can do other things. Okay. So I'm going to list, 5 or 6 different variations of this basic setup that we have seen. So one has to do with optimizing for risk, okay, or in some way incorporating the variance of the rewards into the objective. So, instead of saying it technically, let's just look at an example, right? Suppose you have 2 arms, and one is going to give you rewards of 0 and 100, okay, each with probability half. So if you pull it with probability half, you get 0, with probability half, you get 100. There's another arm which with probability half gives you 48, okay, as the reward, and with remaining probability gives you 50. It's not too hard to see that arm 1 has the higher expected reward, okay, which is 50. Arm 2 has an expected reward of 49, okay, which is less than 50, and therefore it's a suboptimal arm, etc. But the question is, which one would you prefer? Okay, suppose I told you to play the bandit, right? Would you play arm 1 or arm 2? It's really up to people's choice. Who knows? If you have like lots and lots of time to play this game, right, you might play it multiple times, then you'll probably go with arm 1. But if you have, let's say, just one chance at doing it, you'll say, well, give me 48 rupees assured. Okay, I don't want 0 or 100, give me 48. Okay, so there are, of course, ways to formulate the problem differently and try and optimize for some measure of risk minimization. Okay, on bandits, it's usually not as elegant and easy as it is to minimize the expected cumulative regret, because expectations, like sum of expectations, an expectation of a sum is a sum of expectations, right? That doesn't happen when you bring in variance. So it gets a little bit difficult, but you can still do it. There are studies. yet another question is, what if the means of the arms, the true means, right, themselves change with time? Okay, so this, for example, happens with online ads, right? As soon as an ad is published, people are interested, maybe they click, but over time, right, people maybe have seen this ad and their interest slowly wanes off. Okay, so there can be like a gradual drift. Sometimes there can even be a sudden change. Okay, and in reality, this does happen, and this is what's called the non-stationary setting. So stationary means you stay put. Non-stationary means the mean wanders around a little bit. Okay, so there are approaches to model the non-stationarity itself. Okay, you have an additional model saying this is how the means change with time. In practice, maybe just a very simple thing to do is don't trust very old data. Just take your most recent data and say that, well, things couldn't have changed by so much in the last few hours, right, or last 1 week, depending on your application. So maybe you just ignore successes and failures you've seen from before that, and just use your most recent data as the data you have from your arms and do your sampling based on that. Or instead of ignoring, you can also do something called exponential weighting of your history. Okay, so in practice, there are ways to deal with this. But yeah, practice also is more complicated. There are many things that usually you won't cover in a nice sort of academic module on this. I mean, for example, who said the set of arms, right, in a bandit is going to stay the same? If you're doing online ads, somebody will give you a new ad to show, right, which you have to show. It's a new arm, and some old ads might get retired. Okay, so things will keep being born and dying, right, and you have to do your sampling in the face of that kind of churn. Again, there are practical ways of dealing with these things. All right. Now, for a somewhat more serious topic, right, which has also a fair amount of attention in the literature, this is called the pure exploration setting. Okay, so remember that when we wanted to minimize regret, we necessarily had to balance exploration and exploitation, right? But here is a setting where there's no need to exploit. And why does this happen, right? So think, for example, of a company that is developing a product for some application, right? Now, there is a phase where they are testing the product, okay? And the assumption is that they will test it, reconfigure it, make it as sort of good as possible, and thereafter it goes live. Okay, so once it goes live, usually you don't touch it. Okay, the population will use it, right? So the process of testing, right, is one in which it really doesn't matter when if you're making changes that work or don't work. Really, what matters is at the end of the testing phase, right? You should have something that is as good as you could have made given the constraint you had. Okay, so there are usually two different formulations in the pure exploration setting. One is called PAC. PAC is something you've probably also heard in other machine learning contexts. It's probably approximately correct. The problem here is with probability at least 1 minus delta, right? Your algorithm must return an epsilon optimal arm. Okay, an epsilon optimal arm is an arm whose mean is within epsilon of the highest mean. It need not be the optimal arm, but it should be close enough. Okay, but in order to identify this arm, you should try and pull the fewest number of times. Okay, so because sampling, right, running experiments is costly, so you want to minimize that. At the same time, with high confidence, you want to identify something that is close to optimal. All right. Now you can imagine, right, that the actual number of pulls you need will depend on epsilon and delta, and that's usually the kind of sample complexity bound that is given in sort of the PAC formulation. All right, but see, the point is it doesn't matter if you're pulling arms that are bad while you're doing PAC. All right, because nobody is counting your rewards. You're counting the total number of pulls till you stop and say this is my answer. Okay, and that answer has to be correct in this PAC sense. Sort of complementary formulation is called the simple regret formulation, where your input is not like the mistake probability delta, but the number of pulls, okay, the horizon or the budget T. So you're given T and told do whatever you want in these T pulls, but at the end of this, you give me an arm A. I will see how good A is by comparing it with the optimal arm. Okay, so what I would like to maximize is the expected value of P star minus PA. Or rather minimize that value. Okay, so that quantity, right, is called the simple regret, and you want that to be minimal, which also means you want expectation of PA to be large. Simple regret is also a very natural formulation in these practical settings. You might have like 3 days to run your experiments, right? So 3 days is going to define the number of pulls you have. Do your best. At the end of it, you want an answer that's as good as possible. Again, you don't need to exploit while you're doing this. So there's a fair amount of literature in the pure exploration setting that you can look at if you're interested. A much older problem, all right, that people have studied, especially in the operations research community, is what if we had only a small number of stages of feedback, okay, while experimenting with our bandit. So what do I mean by a stage of feedback? So the algorithms that we have seen, right, let's say UCB or Thompson sampling, what happens? You do a pull and then you see the outcome of that pull. Was that a 0 reward or a 1 reward? That goes back into your decision making, right? So the next time you make a pull, right, your history has been sort of incremented by 1 and you can look at the new history to make your choice. Okay, so essentially these algorithms are what's called fully sequential, in the sense that every time you play something, you can use the outcome of that in deciding what to do next. Okay, but in practice, you might not get feedback as regularly, right? It might be delayed. You might only be able to see what happened as the outcome of a pull much later, right? So assume that you have a horizon of t, right? But only at some s, which is a smaller number than t points, you can actually look at what has happened. Okay, you can look at the rewards that you got up to that point. So an extreme case of this is just taking s equal to 1, right? So s equal to 1 means you have to pull your arms. At some point, you can see what rewards in aggregate, right? You can look at all the rewards that have been accrued based on what you pulled. Use that to make your next choices of pulls, okay? And that's it, okay? There's no looking after each pull what going on. So that's just like a single stage setup. I mean, things like this have also been studied, okay, in the literature, but then you can have multi-stage as well. In practice, it is often the case that the sheer number of arms in a bandit instance can make it problematic to learn anything meaningful. So we spend a lot of time trying to show that UCB has logarithmic regret, right? We know that that was the best you could do in terms of dependence on the horizon. But notice that the same regret bound, the accompanying constant, right, is linear in the number of arms in the bandit. So each arm is contributing a little bit. And that is not really very meaningful if the actual number of arms runs into, let's say, thousands or millions. But that is often the case in practice, right? You might have like 10,000 possible ads that you can show on a certain web page. So what do you do about it? Well, it is also often the case in practice that you can say that there are these two arms that are similar in some respect. Similarity usually being described by the fact that maybe there is a common feature, right? Maybe both of these arms are advertising vehicles. Okay, one is about a car, another one is about a bus. So you can expect that the click-through rate of one ad, right, should somehow be similar to the click-through rate of the other. So you can take this a step further and make an assumption, for example, that there is a linear combination of these features describing the arms, which describes the reward function, right? And therefore, what you will end up learning is the coefficients of this reward function, which is a smaller number than the actual number of arms. Okay, this is what happens in what's called linear bandits. Yet another approach, which I'm calling here quantile regret, is somewhat different. Okay, so the case is, even if you have a million arms, whatever number of arms you have, if you pick, let's say, 10 of them uniformly at random, right? Pick 10 arms uniformly at random from a large set of arms, with expectation 1, right? There will be 1 from the top 10%, okay? Rather, the expected number of arms you'll get from the top 10% is 1. And that does not change whether the number of arms you're sampling is 100 or 1,000 or million, right? And very often, if you're getting an arm from the top fraction, that might be a good arm, right? You might not be able to compete with the best arm, right? But quickly enough, you should be able to compare with better and better arms. Okay, so this is the idea in quantile regret minimization, which is really the work of my PhD student Arghya Roy Chowdhury, who is due to graduate soon. So if you're interested in this idea, we have a bunch of papers having to do with regret as well as PAC. Please look at my web page. Yet another configuration that happens in practice, sometimes you might be dealing with multiple bandit instances. Okay, so imagine that there are many possible users who are logged into a website. You have to decide for each of them, should I show them a sports page or a fashion page or a news page? So if there is reason to generalize from one user to the other, right? Again, maybe these users have shared context, maybe in terms of their demographic, maybe in terms of their browsing history. Whatever you learn on one user or in one context, you can probably extrapolate on another context. Okay, this forms the basis of what's called contextual bandits. And contextual bandits are a nice in-between for going from regular bandits to reinforcement learning. Okay, so reinforcement learning also has something like context, but there is also additional sequential dependencies among the contexts, which contextual bandits does not have. Last but not least, okay, so there is a whole area of bandits that's called adversarial bandits. Okay, almost you can say that what we saw, right? Stochastic bandits is one half of the story. The other half is what's called adversarial bandits. The idea here is that there is no statistical assumption made about the way the rewards are generated. So what we have done in this course is assume that there is a stochastic process, right? Each time you want to get a reward, that process is executed and it gives you the reward. But that might not be the case. Okay, so I mean, one small departure from that we've already seen is when there is non-stationarity. Maybe the parameters of that process change slowly with time. But I mean, you could go further and say there is no such assumption you can make. Maybe there is another agent who is doing something and that is affecting what rewards you're getting, right? And if that agent is, I don't know, doing something that changes with time, maybe actively countering what you're doing, then the stochastic assumption is simply not valid, right? So you make no assumption about sort of the stochasticity of the rewards. It is still possible to achieve sublinear regret. Okay, here you have to be a little careful and define regret as the difference between playing the single best arm, okay, against a fixed adversary. So subtract from that what you get by actually learning on the job as you do, right? So it's possible, although it sounds a little bit counterintuitive, to do better than getting linear regret. But one key aspect of any successful algorithm for the adversarial setting is that it must be purely randomized, in the sense that it cannot be deterministic. Any deterministic algorithm can be completely outwitted by the suitable adversary, right? On the other hand, if you put your eggs in multiple baskets, then I mean, whatever the adversary is expecting you to do, you can always do a little bit outside of that, right? So they cannot sort of optimally counteract what you're doing. And so in that space, right, you're able to make progress and you can actually show sublinear regret. Okay, that's for another day. For those of you interested in adversarial bandits, maybe you should follow Manjesh's course in IEOR. Okay, all right, so this looks like slide 27 out of 27. Okay, which means we're done with this lecture. We're done with bandits. I want to conclude with maybe a word of caution, or maybe just a bit of advice. Okay, I'm not going to be surprised if many of you are wondering, you signed up for an AI course, right? Not for a mathematics course. What's going on over here? You're seeing slides full of equations. Now, the fact of the matter is modern AI, right? A lot of its success has to do with the fact that at its heart, there is a lot of rigor, formal modeling, and analysis that sort of makes sure, right, that algorithms behave, have intended effects, rather than the somewhat old-fashioned method was to do things in a more ad hoc way, right, and empirically test. Here, right, to the extent theory can help, we are appealing to it and using it. Okay, so many of us, I mean, look at applications of AI through, let's say, media, right? I mean, you talk to your phone, you hear of cars that are driving themselves. I mean, it comes into our lives in the form of recommendations made on websites. So this is all the fancy stuff, right? It sort of draws you in, but how does it work, right? The actual behind the scenes working is the nuts and bolts of mostly mathematics and very careful, rigorous analysis to the extent you can. So theory is not always doable, right? There are, of course, gaps between theory and practice, but my own philosophy, right, and to a large extent the philosophy of modern AI is to abstract out mathematically and see how far mathematics can take you. That mathematics you've seen is probability. There is also sometimes linear algebra, optimization, etc. Okay, so I would say embrace it. Okay, you can pick it up, right? It'll be a good investment for you to make to try and get to the bottom of these things, because it'll take you far more. All right, so we are done then with week 3. I'll see you again in week 4. Bye.